So we'll take up some special problems in moment distribution. One such special problem is this. So wherein you don't have any member load, only a sway load is being applied on the rectangular or orthogonal frame. So in this particular structure, it undergoes only sway. Only sway analysis has to be done. So the procedure for analyzing such pure sway frame is similar. First you have to identify the unknown member forces which you have to determine during analysis. So that is as usual, the unknown member forces are MAB, MBA, MBC, MCB, MCD and MDC. These are the unknown member end moments which we are determining during analysis. And of course shear forces can be determined and once we know the end moments. Then, so regarding the unknown displacements, here in this particular frame, so the unknown displacements, here at A, all the three displacements are 0 because it is fixed. Similarly, at D, all three possible displacements are 0 because that's also fixed. When you come for this B and C joins, the vertical displacement, it is not possible because at B, if this B end moves up or down, for the member BA, he also should move up or down, which is not possible. So this vertical motion is not there. Same thing here at joint C also. The vertical motion on same argument because member CD, if C undergoes vertical displacement, they also should undergo same type of displacement which is not possible. So this also should be 0. And of course rotations are there, that is theta B, theta C. As for translation is concerned, translation it can undergo because there is a load also. In that direction of load itself, it can just move like this by same amount, delta, delta. So the unknown displacements are theta B, theta C and delta, and hence this is a sway type of frame. Since it is sway frame, by moment distribution you have to do 2 times the moment distribution analysis. That we will see. Next, second step, distribution or distribution factor. So the distribution factor at A and D, it is 0. Only at B and C you have to evaluate the distribution factors. The joint B and C, the members at this B and C are BA, BC at joint B, and C you have CB and CD. So either you can take stiffness or relative stiffness value. Now as a change, I will take stiffness itself. Just let us see whether they are same. Instead of relative stiffness, I will take the stiffness value itself. You know the for member BA, one end is fixed, other continuous. Stiffness will be 4EI by L. 4EI is 2EI, so it is 8EI by 6, it is 4EI by 3. Similarly for BC, both ends are continuous, it is 4EI by L, that is 8EI by 6. 8EI by 6 means it is 4EI by 3. CB, it is same as BC, it is 4EI by 3. Then when you come to CD, same thing, it is one end fixed, other continuous, so it is 4EI by 3, 4EI by L. So the total stiffness, here it is 8EI by 3, here 88 by 3. So this is total stiffness and distribution factor K by sigma K. That is 4A by 3 by 80A by 3, it is half. Here also half. Same thing at joint C for member CB, distribution factor will be 4A by 3 divided by 80A by 3, half. Then for CD also it is half. These are the distribution factors. Then third step, let us take up non-sway analysis. Non-sway analysis. So for this non-sway analysis, first you have to find out fixed end moments. Fixed end moments you are determining for the loading coming on the member. Here, no member has a load. Member AB, there is no member load. BC also no load. CD also no load. But this load is acting at the joint, not on the member. So there are no member loading. Hence, fixed end moments are 0. That you can say. Since there are no member loadings, fixed end moments, FEMs, they are 0. Hence, this non-sway analysis need not be done. All non-sway moments will be 0. All MAB, MBA, MBC, MCB, MCD, MDC due to non-sway, it will be 0 only, because distribution cannot be just carried out because no moments are there. Hence, non-sway moments are 0. Moments are 0. That is the speciality of this particular problem. Next, fourth step, you have to do sway analysis. Sway analysis. Since non-sway analysis gives 0 moment, only sway analysis gives you moments, and that is why this particular frame we call it as pure sway frame, and the analysis is called pure sway analysis. The previous problem, it is sway analysis. This is pure sway analysis. Other problems what we did, beam and other thing, non-sway analysis. So 3 types of problems you can expect. In the sway analysis, first you have to find sway moments. Sway moments develop at the ends of members which undergo sway. Here, which are the members which undergo sway? Member AB, it undergoes sway delta. So this member AB, it undergoes sway like this. So we have to fix the ends of the member AB like this, and sway load is there like this. Because of that, we have to find the sway moment. Since sway load is like this, there will be forces developed here at this fixed end in this fashion, which gives a clockwise rotation. To oppose this, there must be fixed end moments developed at the 2 ends in this fashion. Applied is the moment is like this. This is resistive moment, anti-clockwise. Both moments here at the ends, they are in the same direction, and their values also same, and that will be equal to 6EI delta by L square. This is arbitrary sway we are giving, arbitrary value. So this moment will be 6EI. EI is 2EI. 6 into 2EI delta divided by L square. L square is also 6 square. So this value will be EI delta by 3. And of course, it is negative, anti-clockwise. Same thing with the other member which is undergoing sway, that is CD. This also undergoes sway, CD. So this also you have to fix it. So there will be forces acting like this. Force has to be here to cause this particular sway. Since a force is like this, to keep this in equilibrium, there must be equal and opposite force here like this. But this gives a moment. So to oppose this, there will be moment developed at the ends in the other direction. Now this is perfectly in equilibrium, and this moment developed is 6Ci delta divided by L square, that is 9. So this is 2Ei delta by 9. This is also negative because it is anticlockwise. Since it is arbitrary sway, we have to take the relative sway moments MAB, MBA, MCD and MDC bar. That will be, this is minus Ei delta by 3, this is minus Ei delta by 3, this is minus 2Ei delta by 9, this is minus 2Ei delta by 9. These are the sway moments, or 2Ei delta by 3, sorry. This 6 by 9, so it is, if I divide by 3, this will be 2, this will be 3. So this is 2Ei by 3, 2Ei delta by 3. Or if you multiply this by 3 by Ei delta, you will get minus 1 is to minus 1 is to minus 2 is to minus 2. So these are the arbitrary sway moments developed in these members AB and CD, which undergoes arbitrary sway. You carry out this sway moment distribution. Next, please step sway moment distribution. That is for that sway moment. So you prepare the table. So join member, then distribution factor. So joint A, only one member AB, and joint A is fixed, so distribution factor is 0. Joint B, two members BA, BC. Distribution factor for BA, it is half. For BC, it is half. Next, joint C, CB, CD. Then distribution factor, same half, half. Then lastly, joint D, member DC, since it is fixed, distribution factor is 0 for that. Then write arbitrary sway moment. Arbitrary sway moment, whatever you have determined here. So in AB it is minus 1, BA it is minus 1, and BC, CB, that is not undergoing any sway. We have not determined any sway moment, that is 0, 0. Then CD, it is minus 2, DC, minus 2. These are the arbitrary sway moments. Then we have to do balance. These arbitrary sway moments we got by assuming the ends of the members fixed, as we do in non-sway analysis, same thing, by undergoing sway. So do the balance, that means these moments we got by taking ends of the members fixed. But actually in the problem, ends need not be fixed always. Only some may be fixed, some may not be fixed. Here joint A is fixed, joint C is fixed, but B and D are not fixed, they are continuous. We have to do the balance. So here joint A it is fixed, no balance. Joint D fixed, no balance. Only joint B and C are not fixed. Whatever that error which is you got here by assuming that to be fixed and obtain this moment, that has to be balanced. That's the actual basic principle of this moment distribution, balancing. Here, how to do the balance? So we apply equilibrium condition. Sum of the fixed moments of all the members should be 0 at that joint. So here MBI is -1, MBC is 0, which are meeting at D. Sum is -1, balance moment should be +1. The +1, which is moment which is there at joint B as balance, that will be shared by these two members in proportion to distribution factor. That is +1 into half, that is 0.5, +1 into half, 0.5, they are the balance moment. Next, go to joint C. At joint C, MCB plus MCD has to be 0, but this is not 0, it is -2. Balance will be +2. +2 into half, it is 1. +2 into half, 1. So they are the balance moment in the member CB and CD coming at the joint C is the moment. Now this equilibrium condition is satisfied. Next, this is cycle 1. Next we will go for cycle 2, because these balance moment whatever we have that are there in the members coming from one end. In the member CB, this is the balance moment coming from C. It will have an effect at D end of the member, that we call it as the carryover. That effect is half that particular value, so that we will carry over for each. For AB, there is no balance, so no question of any moment transferring from AB to BA end. So here it is 0. BA to AB, half this value, say 0.3. 0.25, I will round it up to 0.3. Then BC to CB,
0.3.
so it is also 0.3 because it can be carry over. It can be done. Carry over need not be done if at all the other end is hinge or roller or simply supported. Here all are fixed and continuous. Blindly you follow the carry over process. CB to BC 0.5, then CD to DC 0.5, DC to CD, it is 0. So this is carryover. Next, again, because of this carryover, whatever balancing or equilibrium you have satisfied, that is nullified now. Here you have your big equilibrium condition is not satisfied because some of the moments is 0.5 now. Again you have to do the balancing work. So again repeat it. At AB no balance because that is fixed, same procedure. Here it is 0.5 is the sum of the moment. Balancing moment will be minus 0.5. So minus 0.5 by 2, it is minus 0.25 minus 0.25. Here it is 0.3, so it is minus 0.15 minus 0.15. Here nothing. Then you can do one more carry over. Here to here 0, here to here it is minus 1,3. Then here to here minus 0.13, here to here minus 0.08, 0.75, it is 0.8. Then here to here minus 0.08, here to here it is 0. Then balance nil. Here minus 0.04, minus 0.04. Here it is minus 0.065, minus 0.065. Here, nil. So you can stop because these balance moments are all small. In the earlier problems, balance was automatically stopping. Here, you can stop at a stage then that balance moments becomes very small. That you have to observe in this problem. Then you can find out final sway moments. You can find out final sway moments. I will add up. So I have the value here. It is -1 plus 0.3 minus 0.13. It is minus 0.83. Right?
Yes, sir.
Minus 0.83. Then here it is minus 0.71. Here it is plus 0.71. Here if you add up, you will get 1.00085. 1.085. Here minus 1.085. Here minus 1.58. Check up these values. I hope it's all right. So this is the sway moments what you are going to get. After this last step, you can plot the bending moment diagram for this particular sway frame. So you can write this frame. You mark all the member end moments.
So here it's an arbitrary sway value.
That of course I have to do.
It has to be x times.
That before this I will do it.
Yes.
Now this is next step. That is final sway moment. Final. That is what I was doing here.
Yes,
Final moment. Final moment at the end. That is fifth step. Final moment. So MAB is equal to MAB non-sway plus MAB sway. As usual, here this is due to arbitrary sway. We say let the actual sway moment be x times this arbitrary value. Let actual sway moments be x times x times the above value. So these are all due to arbitrary sway. So actual sway moments be x times this. So therefore final moment will be MAB non-sway. Non-sway moment is 0. Sway moment is minus 0.83x. Then MBA will be minus 0.71x. MBC plus 0.71x. Automatically MBA plus MBC is 0 and MCD is 1.085x. MCD minus 1.085x and MDC is minus 1.58x. These are the final moments. You have to evaluate x by applying that sway condition. So to find x, you have to apply sway condition. That is, you mark all the loading, external loading which is causing sway, as well as the reactions develop. Reactions develop, you indicate in the positive direction of the coordinate axis chosen. So this is HA, HD, and this is 20 kilonewtons. So you apply the sway condition. Sigma H is equal to 0. So therefore HA plus HD plus 20 equals 0. All in the same direction. This HA, as I told you, is nothing but the sum of the end moments at the bottom at which this HA is acting. That is MAB plus MBA plus moment due to any load on that AB about the top end. There is no member load, so that moment is 0. This divided by height of the member. Similarly, this is MCD plus MBC divided by height is 3 meters plus this 20 I will take it to the other side. It is minus 20. Here you can simplify. This will be 6 is the LCM. So this is MAB plus MBA plus this will be 2 times MCD plus MDC is equal to minus 6 into 20, that is 120. So MAB plus MBA, you substitute this value, it is 0.83, 0.71, it is 1.54 minus 1.54 x. Similarly, MCD plus MDC, that is minus 2.665
into
that into
5.33.
2, that is equal to
5.33, sir.
5.33 x is equal to
Minus 1.
minus 120. Now you can simplify and solve for x. X value you are going to get, I think,
17.46.
17.46 minus plus 17.46. So substitute this value here, you will get MAB, MBA and all those things. So therefore you will get, after substituting, therefore MAB you will get 0.83 into 17.46, you will
Minus
get
15.
minus
Minus 14.49.
14.5.
Yes, sir.
Minus 14.5. So here I will mark that moment, it is minus, so it is an anti-clockwise, 14.5. Then MBA
Minus 12.4.
minus 12.4, that is minus means it is anti-clockwise, like this 12.4. Then MBC
Plus 12.4.
plus 12.4, obviously MBC is clockwise like this 12.4. Then MCD I think you will get
18.9.
MBC over MCB is 18.
18.
MCB is 18 and MCD
Minus 18.
minus 19, I think.
Yes, sir. 18.94.
MCD minus 19 and lastly MDC you will get minus 27.6. These are the final moments. You can substitute here. This is CB, it is 19 clockwise. Then CB 19 clockwise, CD minus 19 means anti-clockwise, and this is minus anti-clockwise
27.6.
6. So this you can plot as bending moment diagram. So that's the last step. So you can take that each member individually like this. You plot on the tension side. Here it is 14.5. Here it is 12.4. You can join 14.5, 12.4. So this is negative, this is positive. Then here 12.4 down by same amount. Here it is 19. You join that. This is 19, 12.4. This is negative. This is positive. Then coming to this 19 is this side, and this side it is 27.6. Join that. So this is positive, negative. So this is your bending moment diagram in this particular frame. This completes the analysis of pure sway frames. So this is one special problem which I wanted to work. So next, another special problem is symmetrical frame analysis that we will take up next. So most of the